I think we are discussing space diversity. This diversity is a simple variant of MIMO. Uh, MIMO refers to the use of multiple antennas, and uh, it has many different uh, categories, and one of them is called receive diversity. And a simple type of receive diversity is what we are sharing now. So this is, you can say, the simplest variant of MIMO, and oftentimes people even don't use the term MIMO. Rather, they just use this diversity or selection diversity term because most MIMO techniques are too complex. Later in this course, we'll discuss MIMO, the most popular uh, types of MIMO to some extent, just to get you guys familiar with those types. However, this current discussion is included here because in our country, MIMO has not been deployed yet, to my knowledge. But this, I mean, the complex types of MIMO, but this variant, which is more, I mean, commonly just called diversity, is available. It's deployed in many places in our country. Um, Now, the the first type, space diversity, we already explained, and um, so here we had two receive antennas and one transmitting antenna at the base station. Uh, but we can put them together, and like here, see, here it's using two boxes. These are actually boxes with the actual antennas inside, and the antenna elements uh, represent the. I mean, the antenna can have multiple elements to form an array. Okay, so here we can see two boxes because there are two antenna arrays, one for certain lower frequency band, the other for certain higher frequency band, maybe for 900 and 1800. And we know that for 900 band, our antenna elements will be bigger. So for 1800 is smaller. So this is why you have two different boxes. And now you can see that there are two antennas, and one of them, I mean, the left uh, three can be connected, uh, and they form not connected, but they form one array, and the right three here on the left side form another array. So this is how you have two antennas, which you need here for reception, like two. And I mean, you can use one of them for transmission. Okay. So this is like, I think once I explain the other part, it will be better clear. And here you have again uh, the same kind of, I mean, five elements are forming one array, but we have two antennas in a box, uh, just to have two receive antennas to implement this selection, this space diversity. Okay. Now, the diversity can be also alternatively implemented using the variation in polarization. instead of using the two antennas with some space, all we need here is to have different multipath environment with respect to the two receive antennas. So the receptions are different, and we'd keep selecting the better one. In the case of polarization diversity, the two antennas are used with two different polarizations instead of two different spatial locations, two different polarizations. Like we can use a combination of horizontal and vertical polarization. For example, here you see that the two receive antennas have two different polarizations. For the first one is vertical, the other one is horizontal. The transmitting antenna is using vertical, and alternatively, you could use this way. This vertical antenna is used for transmission and reception. Transmission and one reception. And the horizontal ones are used for the other reception. Okay, so instead of having two boxes, you could put them here inside one box. When you have two separate boxes, if you implement this way, then you might see the antennas this way. See here it's implemented for three different sectors in three different directions, and you see that you have here TX2 and RX2 or RX2, like, okay, I mean the two receive antennas for sector 2 located here and here. Okay, and so I mean at every corner you have two. One is carrying the two receive antennas, the other is carrying the transmitting antennas. But now let me show you how the boxes you have, like here. Uh, okay, maybe I go gradually there. Hmm. So is the box is the box here is just a casing to carry the signal and carry the antenna. And typically you have multiple antenna elements or an array. Each antenna, like here, you have two antennas in each case, and each antenna has three or five array elements. Here you have four array elements to form one array, and you have either, I mean, uh, you have either trans, I mean, transmitting antenna or receive antennas. Okay, but if you could use this way, transmitter and receiver vertical antennas uh, are not different, rather you're using the same one, then you need a duplexer to separate the signal. You feed signal from one circuit. This is actually a type of circuit, the duplexer, which can separate the signal. So you feed signal for transmission, and that is passed uh, onto the antenna, and from the antenna, duplexer receives signal, and it is for this port for, I mean, is shown as RX1. Okay, this way a single casing can include all the necessary antennas for a sector. So you have just three sectors, three cases for the three sectors. Okay. Now the last option is the most popular one, which we are calling polarization plus 45 minus 45. Population diversity is more popular than the space diversity, and this one is the more popular option within polarization category. Plus 45. So instead of horizontal and vertical, you put the two inclined at 45-degree angle, like this. So as if you tilt both horizontal vertical by 45 degree. So this way, of course, I mean, one of the two, plus 45 or minus 35, would get a better signal. I mean, their signal receptions would be different, and you just keep monitoring them and selecting the better one. In this case, the 3 plus 45, the 3 plus 45 antenna elements form one array, and 3 minus 45, or I would say 3 um, say 3 towards tilt elements form another array. So each array has 3 elements, and the arrow elements for one particular antenna is either rightwards tilted or leftwards tilted. Okay, so you have separate lines for them, and again you need duplexer to separate the transmission and reception. So it may look like casing, but casing is actually a metallic one with the backside uh, working as a reflector. So the antenna has some significant radiation in the reverse direction. I mean, the back lobe is usually significant for antennas, but there is no loss of power for the significant back lobe, because the reverse power gets reflected by the casing, and it's also uh, incident in the forward direction. So the forward power, or the power in the front lobe, in the main lobe, increases because of this reverse power reflected by the casing. And so here the cover is removed, and the array antenna elements are shown inside the casing. But on top of it, a transparent cover is used. So the whole thing looks like this. Looks like this, okay, where you actually have a transparent cover with the metal antenna elements holding the antennas. And in this case, we see separate parts in the casing because you have different antenna elements, like which are connected, I mean, which are used together to form an array. And so they are put separately. Also, it is using 2 different bands. So for 900 band, we know that the antenna elements will be bigger. For 1800, it will be smaller. So here, this one is something for the 1800 band, and here we have array elements for 900 band. In this case, actually these two, I mean, the two through which you have a green arrow is forming the element which is leftwards tilted. And the 2 elements, we see the 4 elements, but actually the 2, a pair of elements through which the blue line is going through which I mean through which a blue line is shown, is forming the rightwards tilted element. So functionally, there are 2 elements here, one leftwards tilted, the other one rightwards tilted. This way you have elements in other parts of the casing, and then they all together are working as an antenna. But of course, leftwards tilted from one array, rightwards tilted from another array. So like here, I can, I mean, probably you can be better explained. Like here, if you look at the left casing, so you have three leftwards tilted forming one array, and three rightwards tilted forming another array. So we have polarization diversity using two antennas. On the uh, in the middle casing, you have again antennas. So the left one is for 900 band. For the middle one, you have actually antennas for a higher band, which is 1800. This is why the antenna elements are shorter. And here each array has 5 array and elements. Now come to the rightmost casing. Here, a single casing incorporates both types of band, both types of antennas. I mean antennas for both bands. So the two small elements are forming uh, arrays for the 1800, and the three elements, I mean, for either say leftwards 900 band array, you have three elements. For rightwards 900 band elements, you have three elements. But in the case of 1800, you have two elements for either leftwards or rightwards forming arrays.
Sir,
Okay, is it clear?
sir,
It's not, right? Are you getting confused?
about the rightward polarized, plus 45 degree and minus 45 degree are both designed to receive or transmit same bandwidth or different bandwidth?
Yeah. Right, you are right. They both are both. Uh, you know what? Only one can be used for transmission because it's using receive diversity. Okay.
Yes, sir.
When you can use duplexer for, I mean, to feed to both for transmission. However, it's actually for receive diversity. It works only in the uplink. The base station receives with two different, I mean, options with two different signal levels, and you keep selecting the better one. So you may use only one of them for transmission, but it is possible that you use both.
Yes.
Okay.
And sir, how is the reflector
But
increasing?
let me tell you that this plus 45 minus 45 is more popular option because it when you receive from the base station, you're receiving from the transmission of your phone. And very commonly, people use the phone tilted when they are, say, talking. They hold it next to the head, tilted. The, I mean, the phone is located tilted, maybe almost 45-degree tilted. So this is why the transmission, the polarization of the transmitted signal match better when the received signal is also 45-degree tilted. However, it can be either tilted leftwards or rightwards. Okay, so that varies among the phones, but uh, it's close to 45 degree, whether left or right. So this is why this, for cellular cases, plus 45 minus 45 works better than than the combination of horizontal and vertical. Okay.
Sir,
Yeah, there was another question. Yeah, please go ahead with your question.
reflector is increasing the main lobe power.
Yeah. See, the antenna elements have the main lobe of course, in the forward direction. But they have, like most other antennas, have significant radiation in the reverse direction. I mean, the backlobe can also have significant power. But we don't want, see, if I look at the sectorization, in this case, when you put the three antennas in three different directions, you want only radiation in the forward direction, right? You have the whole sector ahead of you. So you don't want any backward um, transmission. In some cases, you may want, you may have some, uh, I mean, I'm not talking about this cellular case, okay? Also, it's cellular. In some other applications, you may have some users in the other direction. But in the cellular case, when you are installing the antennas, you have the whole, the way we are showing here, you have the whole cell area ahead of you. So backward transmission um, does not help at all. So this is why it uses a metallic casing, and we all know that the metal reflects the signal best. And you see that it is made with smooth metal casing, so it works like a mirror. So when the signal is incident on the metallic casing behind, the casing works like a mirror, and the signal is reflected towards the forward direction. So the actual power in the main lobe increases. Okay, so it is better power efficient then. Is it clear now?
Yes, sir.
Okay. And so, I mean, this is another, I mean, this is the picture of a practical antenna. And here is the schematic diagram. And probably you can, I mean, it is to some extent clear, I guess. The polar antenna elements are set little differently, but basically you have some large elements working for 900 band, some small elements working for 1800 band, and they may be either leftward shifted or rightward shifted, and that's how you get actually, I mean, some different arrays. So let's say, I mean, you have 4 different colors here to indicate which element is a part of which antenna. Like all these blue ones are actually for 900 leftwards. Okay, all the say light gray are for 1800 rightwards tilted. So they all work together as a single array. So probably you're getting the point that they may be, the antenna elements may be located in a different in many different ways, but you may be implementing some maybe just 2 different bands in with 2 different polarizations. Okay. Okay. So probably now you get an idea about the antennas that you see at the top of the towers. You might be thinking that it itself is transmitting, but it's not just casing or top casing. The actual antenna elements don't look that good. They have these peculiar shapes and they're located inside. So we just see the transparent cover and the metallic casing. Okay. Now, uh, discuss how you may work on the radio network planning for a cellular network. The term radio network planning (RNP) um, is very common term in cellular world. They basically have some optimization of a few parameters. But while doing so, you have two fundamental objectives, which we mentioned earlier, coverage and capacity. Okay. You may be working with different parameters as you do the planning. Okay. You actually design the, the radio network for your different base station attributes. But the goal is to have good coverage at the areas where there may be users, okay, at the positional locations of the users. Well, there may be some place, for example, there may be a lake next to your tower, which don't have any users. And normally there are no users either, so you don't want to cover there. So it's possible that there is no coverage in there. So there can be delivered areas without coverage. But there can be also some places which don't get enough signal because of some clutter type in the area. I mean, for different structures, maybe blocking the signal. And in some places, you don't get enough signal. Okay, so although you wanted to have uh, this, it's called then coverage um, hole. I'm writing in the chat box coverage hole. Okay, so radio network planners have to be careful about any uh, coverage hole, existence of coverage holes within the network. So in the coverage holes, the signal may be very poor or almost zero. The other fundamental objective is to have some satisfactory level of capacity. The signal may be available, but wireless resources may not be. So to ensure sufficient resources, considering the potential number of users. So these two things people have in mind while they set these 7 parameters. What are they? So RNP is basically setting proper values for these things. First of all, location of the base station, where the tower may be located. Secondly, how many sectors you should have. It can be 2, 3, 4, or 6, or omnidirectional antenna. Omni means just one cell around your antenna. So these are the numbers I observed. I didn't find any one with 5. And 6 is also very rare. Most commonly, 3 sectors are used. So I'd say almost in 80% cases. And there's some good number of omnidirectional cells. These are called omnicells. So I'd say there may be, say, 15% cells around maybe omni in the network. But of course, it depends on the deployment. I mean, um, there, we cannot just make a direct comment that you might have. I mean, as I see different variations in from my, I just wanted to give an idea from my experience.
Sir, what is the purpose of omnidirectional cell? Why
Omnidirectional
sectorization
means
is also
you are not sectorizing. If you just put a tower here with an antenna which radiates equally in all different directions. Okay. Then from the tower, you just have a single cell around. Then it is called omni cell. Okay. So it depends on the radio coverage requirements. You may require somewhere, I mean, different shapes. Like when you use these directional antennas, you can give a particular, I mean, a cell shape of the cell the way you want. Some cells can be longer, with longer shapes. I mean, the radiation pattern from the antenna can be, say, narrow and long. Some can be fat and, say, pretty much sort of, say, wide angle, but it is not very long. I mean, the transmit power is not going very far. So different shapes, the three different sectors may have completely different shapes, like the logo of Grameenphone. It comes from this the use of three different directional antennas. The radiation pattern for directional antennas, have the type of shape you see in on Grameen logo. But as it has three shapes with different sizes, okay, different patterns like long or short. So is the case for real deployment of the sectors. But I definitely should mention here that these are quite vague way of understanding, because actually, like light, electromagnetic wave does not stop anywhere. So all these shapes or cell areas are actually overlapping. They're overlapping to some good extent. Okay, but for, I mean, design purpose, you may be drawing shape. The border is the signal, right? So RNP is a long project. A good number of expert engineers work for quite a few months to come up with a good RNP solution for a network before deployment. They use a few software tools. We're going to list the Polar tools shortly. But finally, they come up with these design um, solutions, like where how many base stations you should set up, where they should be located, and the number of sectors under each base station. Then azimuth. Azimuth means the direction of your antenna with respect to north. They don't have to be just 180-degree apart like the way we showed here. Things are never that uniform. Okay, here we showed just 180-degree apart, but in reality, the the angle in uh, and uh, from north, when you give the angle, okay, how many degrees it is, then it's called azimuth. Antenna height can be, say, typically from 20 meter to 30 meters. Okay. Uh, the transmit power, you need to set how much it may be at the maximum. Okay, it may be, say, 30 dBm, 33, 36. At most, I found 49 dBm. But when you go for 40 or above, it's using very large cells, maybe in the rural areas. In the urban areas, the power is not that high. Okay, 40 dBm means 30 dBm is 1 watt, right? So 40 dBm is 10 watt, and 43 or 20 watt, 46 or 40 watt use. 49 is very rare, but up to 46 people use. Okay, then transmit antenna gain, or HPVW, and down tilt. Down tilt is an angle of the antenna with respect to the vertical direction. The antenna at the top of the tower is not located straight in straight vertically. It's because if you think about some watchtowers used for large gatherings, like for a fair or maybe for Istema Field in Tongi. If you have been there, there are some watchtowers from where the cops keep monitoring. Uh, but you know that people are not flying; they are on the ground. So top of the towers, the uh, security people need to look downwards, like so they need to bow their heads to some extent to look at what people are doing. So similarly here, from the top of the tower, the like you go to watch the people on the ground, the antenna is also a little bit tilted towards the ground. So you have a coverage area, uh, limited coverage area. So, so it's like this. And like other things, you may have to adjust them. So this is more easily adjusted, like from the bottom you should be able to connect your laptop and send a command, and accordingly the down tilt will change. The change may occur either with mechanical control or electrical control. By mechanical control I mean, so the hinge uh, I mean changes its angle as you send a command. So there is a mechanical rotation here to adjust the angle of down tilt. The other option is to use the array. Uh, I mean, it is sometimes it uses phased array. So the signal fed to different array elements have some phase differences. That's how it works. But it's possible that you change these phase differences and change the direction of antenna radiation. So, so this is actually a strong option for antenna control. You don't always have to rotate an antenna. Rather, even in the case of, say, radar operation with rotation over a small angle, you don't have to rotate mechanically. The alternate option is to have use some gradual change in the phase differences among the feeding lines, and that's how the antenna keep radiating in different directions. Like in mobile, there are some MIMO techniques which use this kind of concepts. So it may be transmitting towards you within the cell using a narrow beam, and as you are traveling, it will also track you by changing its direction. But this change in direction of antenna radiation is basically done by some change in the phase differences of the feeding lines. Okay? Different array elements get different phase. So, so this is also an option that you can control uh, the down tilt electrically. Okay, so there are few things which you can play around with. It's not like that. You may have some purpose, so there can be multiple options to fulfill that, but each comes with different advantages and disadvantages. So it's up to you uh, how you should manage. For example, to squeeze the cell size, you can either reduce the transmit power or you can increase the down tilt, right? So if you want to make the cell size smaller, transmit power can be reduced, and so the coverage area will get smaller. But the alternate option is to keep the same transmit power and increase the down tilt. Right? Probably you can understand then the range of power, transmit, signal coverage area will get squeezed. So the next day in the class, please tell me the advantage and disadvantage of these two options to change the cell size. Okay, finally, we are listing here use some software tools used in the current market. Like for this radio network planning, different types of tools are used. It's a basic type of RMP tools, but in addition, there are some simulators can be used to optimize a few things. First, the tool can even work together with the simulation tools. One of these tools, Forsk Atoll. Forsk is the name of the vendor. Atoll is the software name. Uh, will be demonstrated in the lab class, and there will be setting up different base stations, and then set these things also. You'll be able to set these things for your base stations. You can locate the base stations anywhere you like within that tool and set these things. And then once you run the simulation, it will show the coverage areas with different colors and shades where you have, I mean, higher signal, where you have lower signals. So then you'll see that practically the coverage areas are all overlapped onto each other, and you'll also feel how the signal level varies with distance. Okay. Uh, Now there are another popular types of tools which are used after the deployment, uh, is for optimization purpose or continuous monitoring and improvement or checking issues. So these are some drive test tools. Give me a second, please. Which people install on the laptop, or some of them can also be installed on the phone. Then you keep driving within the cell area and checking power level, the interference, and other uh, many other cell attributes. There are lots of messages exchanged between the phone and the network, which indicate different attributes, and these messages can also be captured. So as you keep driving, the your laptop, which has the software installed, will keep collecting all this data. Of course, you need to have your phone connected to your laptop using your USB cable. Then the software actually collects the information from your phone. Okay. Now, oh, the software vendors have some deal with the chipset manufacturers of the phones. That's how uh, they can collect data from there. But the data can also be further processed to actually determine few things, and the tools which are used to process the data collected by the dive test tools are called post-processing tools or PP tools. So I'm listing the popular tools here from different vendors. And the last one, Actix, have only post-processing tools, and it supports actually the data from all these four dive test tools. Okay, but like Nemo Analyze can post-process only the data collected by Nemo Outdoor. Similarly, XCAP can only post-process the data collected by XCal. Okay. Now, in our lab, we have purchased XCal, and inshallah, we'll have an interesting demonstration later using XCal. You can collect live information. Questions? Guys? Okay. Attendance is very good today. Uh, Not very good, but I mean, it's not bad either. It's almost 100. Uh, Questions?
So, sir.
Okay. Then we'll move to our next topic. Um, it- we'll discuss CDMA technology, and the 3G deployment will be used as an example for this 3G, for this CDMA. And once we complete that, we'll go for our second class test. We have 3 more class tests left, and we're gonna take it the next week. So I mean, this 14th lecture and the upcoming one, the 15th lecture on CDMA, we wanna include both of them and go for a test the next week. The seers can suggest a date.
Sir, next week Wednesday.
Okay, you can just discuss and let me know later. Okay, give a second. I'm opening the CDMA document. Okay, someone needs to mute his microphone.
Sir.
Yeah.
Sir, we will be giving quiz on next week Wednesday. If
Wednesday. Okay. So Wednesday at 2 o'clock, inshallah.
Okay.
1 week from now. Okay. CDMA was a big blow in the beginning of this century. Um, we discussed 2G, which uses a combination of FDMA, 2DMA, FDMA, and TDMA. And this frequency division multiplex and time division multiplexes was, considered the only way to share resources among multiple people. But CDMA gave a new concept. Currently, LTE does not use CDMA for this resource sharing. It's true. But there are some concepts where CDMA is still popular. Okay. So the discussion of CDMA still makes sense. CDMA is not an obsolete technology, definitely. There are there are few things which still use the CDMA concept, even in 4G, 5G. Okay, but those are some minor parameters. However, there are other technologies outside cellular where CDMA has some applications. So the concept is still important, and the concept has some underlying strength, uh, and it is amazing. When it was first invented, people are amazed. This is because you see that in the case of TDMA, FDMA, we first chop the radio resources into different parts, and in the case of TDMA, at different time slots, we let the users use them. But in CDMA, the whole bandwidth will be used by everybody. Very surprising. Everybody, meaning that uh, everybody will be using the same frequency range. Also, in time domain, there will be no splitting. So it means everybody will be using the same bandwidth, the same frequencies at all times. Then how can it work? It should all interfere with each other, right? So how can it work then? So this is amazing, but this is the reality. So we'll explain, and but please be attentive to get the concept. In our country, there is some myth about CDMA, and there are some misconceptions. Okay, so even among the wireless folks. So if you are attentive, then you can get the right concept here. Okay, there is an example which can explain the uh, basic, I mean, explain the basic concept. Like if you are in a party, or maybe you think that in the classroom there are many people, and you have different pairs who are talking to each other. Okay, so maybe say you have 50 people, but the teacher is not there. I mean, the class is yet to start, and so someone is talking to his friend, and so this way there are 25 pairs. Then it can be difficult for you to understand your friend because everybody is talking together. So the sound from others may disturb you. So it may be difficult for you. But now you think that if everybody every pair uses different language, then it might be easy for you to understand your friend. Other people around yourself uh, are using other languages which you don't understand at all. If it is the case that they use different language and that is not at all understandable for you, then you can understand your friend easily because he's using the language that you know, you understand. He's using, say, Bangla. People are using Chinese, French, which you don't understand. So although you can hear them, you can still separate what your speaker is talking to you, right? You can separate. So the same way CDMA works, everybody uses separate codes to, I mean, their signal is coded differently, and the codes from others are like which make things uh, things uh, not decodable. I mean, which cannot be decoded. So you can only understand your own transmitter. He is using a code which is known to you, and you can use it to decode your speaker. But other people are using other codes in which are absolutely not understandable. So uh, now let us get back to our example. If it is another pair is using a language which is somewhat close to yours, like you are using Bangla, I mean your pair using Bangla to talk to each other, but another pair is using Hindi, then it may get a little more difficult for you to understand your friend because there is some similarity, right? You know the similarity. Um, I mean, it sounds like when you tilt Bangla a little bit, it becomes Hindi. Like, say in Bangla, we call juta. So if you tilt a little bit in Hindi, you call it jute. So, I mean, there are some similarities. So then it may get a little difficult, right? Similarly, in CDMA, things work fine when the other codes are completely orthogonal to yours and they have no correlation. Okay. But if the other code, if someone else is using a code which is not fully orthogonal, okay, then that can make your understanding little more difficult. So sometimes it is not fully orthogonal, and then that reduces the understanding capability. Okay. Uh, so you may want to make all the codes uh, orthogonal to each other, but it may not be always possible. Okay, so this is the basic concept. And the point is that uh, so far, are you understanding me, guys? Guys,
Yes, sir.
can you follow me? Okay. Now, and the point is that if a pair keeps talking uh, pretty loudly, then it, I mean, his listener, the listener in this pair, can understand very well, but all other users will be affected. Uh, so think about just a cell, okay? The compared with the room we are talking about. So all you other users in the cell will suffer then. They all will get it more difficult to understand their transmitters or their speakers. So everybody should use, I mean, the sound level barely as much as necessary. Okay. In the case of say FDMA, TDMA uh, uses within the cell, at least within the cell, yeah, we definitely discussed that the power level should be well adjusted in the cellular case because it would interfere some other neighboring cell. But here, currently, we are focusing on a single cell, the implementation within the cell itself. So if you think about just the cell inside, then in FDMA, TDMA, you don't have that problem of high power uses. Your high power uses does not uh, adversely affect other users. Okay, they are fine because they are using different radio resource or different time. At least theoretically, there is no problem with the other people within the cell. But in CDMA, that's not the case. Okay. Within the cell, I mean, um, a good part of this discussion will consider just a single cell. At the end, we'll go beyond the cell. Okay. So here, the sound level has to be well controlled. Okay. If you use higher sound, then other people will be difficult. So there are two ways which can make a, uh, I mean, make another pair. Uh, the, I mean, the understanding of another pair difficult. One is the first one that one is what we mentioned earlier, that the language is not completely different. I mean, the codes are not fully orthogonal to each other. The correlation is not zero. There is some correlation. The other case is that the sound level is little higher. That can also cause problem to others. Okay. So now, uh, what kind of code you may assign to different users in the cell? Okay, this is codes are some bit sequence, and the sequence these sequences are called pseudo noise sequence. It is these sequences are sort of random, but there is some sort of actually bias. Okay, some inherent bias within the randomness. So this pseudo noise sequence or PN sequences are generated using this kind of circuits. Okay, but for now, we just assume that I have, say, here 3 different flip-flops, and every time you have a clock pulse, the input is forwarded to the output, for the flip-flops. And from S1 and S2, you do an XOR operation to get the input of the first stage. Okay. So when you have a clock pulse, S2 becomes equal to S1, S1 becomes equal to, sorry, S3 becomes equal to S2. Whatever you had S2 before the clock pulse, okay, will appear at S3. But uh, okay, so this should be S0. It's mistaken here. S0 is the XOR operation of S1 and S3. Now let's assume that initially you had all ones, the initial state. So in the first clock pulse, S1 becomes S2, S2 becomes S3, and S3 is what you get as the output. So this is this. I mean, output is shown as the output of S3. In the second clock pulse, so you get the input of I mean A0.
Sir, which
Oh, okay. Sorry, it's not mistaken. S1 becomes A0, and A0 is the XOR of S1 and S3. So S1 and S3 is, I mean, both are 1. So you get here 0. Oh, is it XNOR? Is it XNOR or XOR? Okay, let me check. I'll check on that. But in our logic, when the two are similar, the output is 0. Okay, if these two are different, the output is 1. So okay, and then again, so in the next clock pass, so they are forwarded here, and S3 and S1 at this stage are different, 0 and 1. Okay, so you get here the next clock pass, you get 1. So this way, I mean, as you keep moving forward, after 7 clock pulse, you again get the initial state back, all ones. And from there, with further clock passes, the same kind of um, steps would recur, right? Meaning that this sequence 1 1 1 0 1 0 0, they will keep repeating after every 7 steps. Or you can say that you will be generating these sequences with 7 bits. Okay, as you keep going through the clock pulses, these 7 bits will be generated one after another. So this is how the PN sequences are created with certain length. In this case, it is 7 bits long. Now, the two properties of PN sequences are autocorrelation and cross correlation. But the correlation is something you may have covered in other courses, which give you the relative, or I would say the matching level. Okay, how closely two things match. If the correlation is 0, then they don't match at all, which is called orthogonal status. And if the correlation is 1, then they match completely. So, okay, so this correlation has two types. Like if you take a single thing and check correlation with itself, then it's called autocorrelation. But if you take two different things and then check they are matching, it's called cross correlation. Well, how come you do autocorrelation? What is the significance? You just match. Well, here what do you do? We check the same thing with different positions. Like we have here 7 bits. And if I assume that it's like you wrap these 7 bits. So you rotate, it takes 7 bits, and then below that, you take another 7-bit sequence, the same bit sequence, but you take again below, and then keep rotating the second one, like we are doing here. In the first step, you take the sequence and then take the sequence again below, just aligned the same with the same positions. Then do correlation bit by bit. Bit by bit means, say, the first, the bit, say from LSB or MSB, you do the bit by bit positions. So they all must be the same. So you get when they are alike, you get 1. So you get 1. So for all of them, it is 1. So the summation is 7. Then in the next step, the second one, holding the first one fixed, the second is rotated by 1 bit. So then LSB0 comes to MSB, and every bit is shifted rightwards by 1 bit. Then hold it, and then do bit by bit correlation. Okay, so when they're alike, you get 1. When they are not, you get -1. Okay, instead of 0, you're using -1, so you can cancel 1 and -1, 1, -1. So sometimes you get -1, sometimes you get 1. Now you see that there are 7 bits, there are 7, but 6 of them gets cancelled because 3 are +1, 3 are -1. So you're just left with one of them. Okay, so that is the minimum possible. On average, you have, say, 0.14. Then you again rotate. This time also is the minimum. Okay, 3 of them. And in every rotations, okay, after 7 steps, again they will align, and again you get definitely all 1 for all bit positions. So it will again be 7, and the average is 1. But you can see that for all other bit positions, I always had the minimum possibility, the minimum value possible. Okay, the average is 0.14. This one would be 1 anyway for whatever the bit sequence is. But in all other cases, we have the minimum. So this is the quality of a good PN sequence. This is the best autocorrelation, where you have for all other until you align. For alignment, it is 1 definitely for any bits. But if it is not aligned, if it is misaligned, then for other bit positions, you should have values as low as possible. The lower it is, the better it is. So if I plot, it will look like this. So in all other cases, it is very low, and when you complete the 7 steps, you have the value 1. These are called correlation peaks. Correlation peaks will be there anyway, but in other cases, if it is low, then it's better. Why is it better? Then you can actually differentiate better compared to the correlation peak. So if you have a bit sequence, you can hold it next to, say, you wanna identify. For example, the bits are transmitted in a stream. Let me take it is close to 9:15, but we also started 5 minutes late, right? So I'll be done before 9:20. Let me just finish this kind of discussion. uh, say, assume that you have a bit stream flowing, or I mean, it's arriving, and it's actually the repetition of these bit sequences. Now, you want to identify where the sequence starts. How do you do that? The It is done using correlation. You take the right sequence and then keep checking the uh, correlation. Okay, with the first position, you have a bit stream, so you don't. I mean, you don't know where you are starting. So, but you hold your actual bit sequence and then correlate. If it is a good sequence, then until you align, you will always have low correlation values. Once you align, you get the value 1, or you have the correlation peak. But until you do the align, it's always low. That's the good autocorrelation property. If the sequence itself does not offer good autocorrelation, then in some cases you get higher values. And the value can be, say, 0.6 or something. Okay. But in wireless communication, things are a lot corrupted in the air or on the way. So you may not get actual one value when they align, and it can be lower because of some bits in error. And when you are supposed to get 0.6, it may get say 0.8 because of bit error. So in that case, you actually may get confused, because when it is correlation peak, you get 0.8, and when it is misaligned because of error, it was already 0.6, because the correlation property was not very good for the particular sequence. So it is also 0.8. So you think that, okay, it is here aligned, this is the starting point. So you run into an error. Okay. So wireless already corrupts your data or changes the bit status. So if you have a good separation, like the pin sequence here, you have a very low value for all other states, all other bit positions, alignments, compared to the correlation peak. Then you well for it on the way cannot confuse the receiver. Right? So this is the quality of a good autocorrelation property of a PN sequence. Okay. So the next day we'll discuss what we mean by good cross correlation. Okay. But many different PNs by different researchers with the same purpose, that the correlation properties good. Correlation autocorrelation, it gives you values, then it's a better or more popular PN sequence. Okay, questions? We'll go from here the next day, inshallah.
Sir, do we get same autocorrelation for just 10 to 6 for all sequence, or only this sequence?
We used an example to explain the autocorrelation, and deliberately the selected example was a good one. I mean, the best in terms of autocorrelation. Autocorrelation cannot be better than this. In this case, at all other, I mean, for all misaligned positions, the minimum possible value.
Yes.
Okay. But if you change the bit sequence and then try yourself, you'll see that the autocorrelation is not that good. Okay. Change we shared. I'm going to share the PDF one. So if you just changing a couple of bits there, the bit sequence, and then check the uh, check the autocorrelation property, you'll see that it is not that good. Okay.
Yes.
Okay. I mean, when I say it's not good, the other values, some other values will be higher. Like we had always 3 cancelled by 3 and leaving 1 out of 7, right? Sure. We have 7. 3 were plus positive 1. Sorry, 4 were negative 1. So 3 got cancelled by other 3, leaving just minus. That will not be the case. Say maybe say 2 gets cancelled or say 1 gets cancelled. So you get a higher value here. Okay. Sequences are not, it gives you randomness with actually certain correlation property. So there is a bias to improve the correlation property, inherent bias. Anything else? Okay, let's stop here. By the way, tomorrow I think I have classes with section B and section C, not with section A, right? So I'd love to have an online class with section A only, maybe in the weekend sometimes. So the CR of class A, please contact me to schedule a class. Okay? We'll have an online class with you. Okay. Thank you for your time.
Assalamu alaikum, sir.
Alaikum assalam.
Assalamu alaikum, sir.
Alaikum assalam.